Welcome to The Explainer. Today, we are diving deep into the fundamental language of computers, and we're going to use the classic 8085 microprocessor as our guide to figure it all out. So let's just jump right in with a huge question. How does a processor, the actual brain of a computer, know what to do? It really isn't magic. It's actually a super structured process of just following directions. The best way to think about this is to picture a CPU as a master chef, and any computer program is just its recipe book. Every single thing your computer does, from opening a file to refreshing the screen, it's all just a step in a really, really detailed recipe. Now, each step in that recipe, what we call an instruction, it's got two main parts. There's the verb, the opcode, which tells the chef what to do, like add or move. But that's not enough, right? It also has to say where to find the ingredients, the operand, which is just the data it needs to work with. Okay, so here's our game plan. We'll start with the basics of that CPU's recipe book. Then we'll get into how it actually finds its ingredients using 5 key methods called addressing modes. After that, we'll see how it all clicks together to form the language of code. And stick around to the end because we're going to talk about why this old school architecture is still incredibly important today.
All right, let's get into it. Finding the ingredients. To really get how a CPU finds what it needs, we've got to speak its language. And lucky for us, it really just comes down to 2 key terms.
First up is the operand. This is easy. The operand is simply the ingredient. It's the number, the letter, the chunk of data that an instruction is going to use or change or move around. And this is the cool part, the addressing mode. This is the piece of the recipe that tells the CPU exactly how to find that ingredient. Is it sitting right here on the counter? Is it in the pantry? Or is there maybe a little sticky note that tells you where to go find it? That's what we're about to explore. So, the 8085 microprocessor, our guide for today, uses 5 totally distinct methods, or addressing modes, to track down its data. Think of each one as a different strategy, and you'll see each has its own unique pros and cons. The most straightforward way is immediate addressing. This is kind of like the recipe saying, add 5 grams of salt. The ingredient, the number 5, is literally right there in the instruction itself. There's no searching needed, it's just immediate. But here's the trade-off, and you're going to see this a lot. It's blazing fast, because the data's right there. But the catch? Putting the data inside the instruction makes the whole instruction physically bigger in memory. And it's not very flexible. You're stuck with that one value.
Okay, next we've got register addressing. With this one, the instruction is basically saying, hey, the data you need, it's in this specific drawer right next to you. These drawers are called registers. They're tiny, super fast storage spots literally inside the CPU itself. This method is incredibly efficient. Access is almost instant, and the instruction itself is nice and small. But, and it's a big but, the CPU only has a few of these high-speed registers. It's like beachfront property. There's just not a lot of it to go around. Now with memory direct addressing, the instruction gets really specific. It's like telling our chef, go to pantry shelf number 9000 to find sugar. The instruction contains the exact literal memory address where that piece of data lives. So this is a pretty simple way to access a huge amount of data in memory, way more than you could ever fit in those little registers. But again, there's a trade-off. The instruction gets bigger because it has to hold that full address, and it's rigid. It always points to that one specific spot. Okay, indirect addressing is where things get a little clever. It's a 2-step process. The instruction says, look in this register, not for the data itself, but for the address of the data out in memory. It's like finding a sticky note that tells you which pantry shelf to go to. And why do this little 2-step? Well, this extra step gives you enormous flexibility. You can just change the address on the sticky note to process a whole list of data one by one, which is absolutely perfect for loops. The only downside is that it's a bit more complex for the CPU to handle. And last but not least, we have implied addressing. For some instructions, the CPU just knows where the data is. The operand is implied. The chef knows that the instruction flip the pancake always refers to the pancake that's currently in the pan. No need to specify. Okay, so now that we know all the different ways the CPU can find its data, let's see how these addressing modes are actually used to build the instructions that make up a real program. The 8885 processor has a vocabulary of 246 different instructions, and we can sort them in 2 main ways. First, by what they do, their function. Are they for moving data,
doing math, something else. And second, by their length. How much physical space do they take up in memory? And this right here is where it all comes full circle. The addressing mode we choose has a direct impact on the size of the instruction, right? A tiny 1-byte instruction is pretty much just the opcode, so it's got to be using implied or register addressing, where the location's already known. A 2-byte instruction has room for the opcode plus a little bit of data, perfect for immediate addressing. And a big ol' 3-byte instruction, well, that's often for direct addressing, because it needs 2 whole bytes just to store that long memory address. See how it all fits?
So at this point, you might be thinking, okay, this is kind of cool, but why are we talking about a processor from the 1970s? I have a supercomputer in my pocket. And that's a fair question. Well, here's why it matters. These core ideas, the opcode telling a machine what to do, and the addressing mode telling it where to find the data, this is the fundamental DNA of every single computing device today, from your smartwatch to the biggest data centers in the world. The recipes are way more complex now, for sure, but the chef is still following the same basic principles. At the end of the day, understanding these basic building blocks helps you appreciate the incredible dance of efficiency and complexity happening inside the hardware we use every day. Every single choice, like which addressing mode to use, is a constant balancing act between speed, size, and flexibility. And that leaves us with a pretty mind-bending question for the future. As computing starts to move beyond silicon and into the wild worlds of quantum or biological systems, how are we going to tell those machines where to find their ingredients? What will their addressing modes even look like? It's something to think about. Thanks so much for joining me.